So in this lecture we are going to study about the material science. So in material science what we will study about the alloy. So what is alloy? So when the two, let's say, let's pick a color. Okay. So here we have, suppose, one M1 material and M2 material. So these two material can be combined to form what we call as the alloy. And the alloy, we can only mix M1 and M2 when the crystal structure of both the material are same. If the crystal structure of M1 and M2 material both are same, then we can mix it. And there are three conditions of Hume Rothery. Basically, Hume Rothery is a scientist, and he has proposed the three conditions on which, if the condition is met, the alloy can be formed. This means material can be mixed. So, what are these three conditions? One, there is the difference in atomic radius of both the material should be less than 3 percentage. Means the radius R1 and radius R2, the difference in the radius of the two materials should be less than 3 percentage. Second, the valency of both the materials should be the same. Suppose the valency is B1 and this is the B2 valency, the valency of both the materials should be same. Third is the electronegativity and electron affinity of both the material should be comparable. So here is the comparable sign. Electron negativity and affinity. Negativity means is the tendency to attract the other electrons, and affinity is the tendency to attract its own electron. So alloys are always stronger than the pure material, which means suppose we have a material M1 and we have the material M2 and we combine it to form the alloy, then the alloy's property will always be greater than the M1 and M2 individual material. Okay. So strength is different thing, because when we combining M1 and M2 we will get the property of both, and the strength will be better than either M1 and M2. So strength is other thing, but we cannot correlate about the melting point. We cannot say, suppose there is a material having a melting point 200 degrees celsius, another material having the 300 degrees celsius melting point, and if you combine we cannot say it to 50 degrees celsius. We cannot say it lies between 200 to 300 degrees celsius. We cannot say. So melting point, we can only tell about the melting point by looking at the phase diagram. So that is the same thing done here. Melting point of alloy will be independent of the strength. There is nothing to do with the strength and the melting point. Melting point of alloy A B will be either between 300 to 600. Means there is 600 and 300 material. It can be between the 300 or 600, or even less than the 300. So melting point of alloy can be known only by looking at the phase diagram. Now we have used the term phase diagram, but what is the phase? Let's first define the phase. So phase is basically what it's a state of a matter, state of any matter. So it is physically distinct, which means the state of matter should be physically distinct. It should be chemically inhomogeneous. What homogeneous? Inhomogeneous. And mechanically separable. So if we have a kind of state which is physically distinct, chemically inhomogeneous, and mechanically separable, then we call it as a phase. So now we will study some phase diagrams. So there are some material and there are some phase diagrams. So one is the binary phase diagram of type 1. Binary phase diagram means there will be two material, let's say M1 material and M2 material. Or this is type 1. What is the meaning of type 1? Type 1, we are considering that kind of material which are completely soluble both in the liquid as well as in the solid state. So here we are supposing the copper and the nickel. Okay, copper and nickel. So copper is one material and nickel is another material. So copper and nickel, they are soluble in the liquid state, they are soluble in the liquid state, and they are soluble in the solid state. So they are soluble in both the solid, and they are soluble in both in solid and liquid state. That's why we call this as a type 1 diagram. So what we have to remember, we have to remember in the in the copper nickel diagram, we have to focus on the melting point of the copper is 100 sorry 1085 degrees Celsius, and the melting point of nickel is 1452 degrees Celsius. And the phase diagram is not like there is 1085 degrees Celsius and there is 1452 degrees Celsius. We cannot simply add this line like this. Actually, what happened, there will be the diagram like what we have drawn here, in this way and in this way. So above we have the liquid and we have here solid, and then between we will have the mixture of liquid and solid. Okay, so here we write 100 degree 100 percentage copper, means copper here is 0 percentage. So copper on going here it will increases, and similarly we will use the term nickel as a green here. Okay, so nickel become 100% at this point, and it is 0% nickel at the this point. Okay, so this kind of diagram is for the copper and the nickel. So copper and nickel both combine together atomically in liquid as well as in the solid states and produces a single phase. It produces a single phase. Okay. When the two elements combine together and produces a single solid phase, we call it as the solid solution. So what is solid solution? The solid solution means when the two elements combine together and produces a single solid phase, it is called the solid solution, which means we have copper and nickel. When they combine, they produce a distinct, physically distinct phase, physically distinct state of matter, chemically inhomogeneous and mechanically separable. That's a phase, and that phase is known as the solid solution. Any line on the top of the phase diagram that separate a single solid phase with the messy zone is known as the solidus. What is solidus? Solidus means suppose here is a solid and here is the mixture of liquid and solid. The line which separate the solid liquid mixture with the solid is known as the solidus line, and the line which separate the liquid mixture with the liquid plus solid is known as the liquidus line. If any alloy system exhibits larger extent of messy zone, lesser will be the fluidity of the material and hence more will be the variation in the mechanical properties. So messy zone is what this dotted liquid plus solid region is the messy zone. Higher will be the messy zone, what the material of mechanical properties will be highly varying in this region. So one can see easily that if any alloy system exhibits larger extent of the messy zone, lesser will be the fluidity of the material and more will be the variation in the mechanical properties of that alloy. When messy zone appear in the alloy system, so this is a messy zone, it appears in the system, then there will be a range of temperature at which the liquidification and solidification are taking place. So there will be a range of temperatures, for example from here to here. So there is a range of temperature. Okay, at different percentage, at different fraction, this range of temperature is varying. Like here the range is very high, here there is just 1 point, here there is just 1 point. Okay, so there is not a single melting point. For example, the melting point of copper is 1085 degrees Celsius, the melting point of nickel is 1400 something. What is the value? 1452 degrees Celsius. But when we are forming the mixture of copper and the nickel, and the percentage of nickel is suppose C naught, then at that point there is no single point we can tell yes this is the melting point, but there will be range. For example 200 to 250 degrees Celsius, like this there is a range at which the material will be melting. Okay, now let's understand about the tie line. So what is tie line? Means suppose here we have drawn the copper and here we have drawn the nickel. This is the copper and the nickel diagram is like this. Okay, let's take some other color to make you understand. Okay, so let's take the red color. Suppose this is the composition C1, C0 is the composition where we want to find the fraction of nickel formed and fraction of the copper formed. So we will draw a line which is perpendicular to did this and cutting this musty zone. Okay, now we can see nickel is here. Okay, therefore it is like the inverse rule, inverse lever rule. So from here to here, this distance divided by the total distance will give the mass fraction of nickel. So the mass fraction of nickel will be equal to, suppose from here to here it is the core, and from here the total is the core. Then we will write, okay, so what is this? So this is, suppose here fraction is, suppose Cl, and suppose the here fraction is Cs. Then we will write C naught minus Cl, C naught minus Cl divided by Cs minus Cl. So this is the fraction of nickel and fraction of copper. The copper is and on this point, so copper is on this side. So therefore we have to take the opposite side, this one. Okay, that will be the, we can say here, Cs minus C naught divided by Cs minus Cl. So this is the mass of the copper fraction. Okay, this line, this horizontal line is known as the tie line. So lever rule can only be applied. Lever rule can be applied only in the two-phase region, in single-phase region, or in three-phase. Lever rule can be applied only in two-phase region, in single-phase region, and or three-phase region. Lever rule cannot apply. So the basic principle is that there is a two-phase system. Then you can apply the lever rule. For one phase and for the three phase, we cannot apply. So look at the microstructure here. So suppose the liquid is going to solidify, and suppose we are at a temperature A. So at the point A, the micro in the microstructure, it will be all liquid everywhere. Okay, and just the moment we fall below the point B, suppose at this point the B is slightly below the liquidus line, then in the liquid there will be some sites where solid is nucleating. Okay, solid is nucleating, and as we move down, the solid process will, grow, the solidification will grow. And suppose we are going to see the microstructure at the C, then what we will see, we see that the solidification has grown, and the solid has nucleated at larger site. So there is solid group of solid here, and group of solids here, and group of solids here. Okay, and that will be inside the liquid. Okay, so the moment when this solid solution, the boundary of the solid is known as the solid front. So when this front and this front will meet, they will produce the boundary. We call it the grain boundaries. So one funda is there. Diffusion doubles for every temperature rise by 20 degrees Celsius. So suppose we know the temperature is required for the diffusion, higher the temperature, more the diffusion. So if the temperature increases by the 20 degrees Celsius, we can say diffusion will get double. Weld decay happens only in the stainless steel, as shown in the figure. So this is the figure which I have shown here. As okay, this is the figure. Sorry, as shown in the figure. We have already studied about the microstructure ABC. Okay, now let's come. So okay. Following conclusion can be made by using the lever rule. Okay, so what is written? Let's read some point here. Solid start appearing in microstructure at different places. Okay. So upon decreasing the temperature from point B to C. So when we are decreasing the temperature from point B to C, what happens? That is written here. Upon decreasing the temperature, mass fraction of solid phase keeps on increasing. So you can only tell you can tell very simply by just looking at the phase diagram. So mass of the solid will keep on increasing. The moment solid nucleates, percentage of nickel in the solid will be very high. So how can you see the percentage of nickel in the solid is very high? I will tell you. So the moment the solid nucleate means there's a liquid, and the moment the solid nucleates means just below the A is only liquid. Okay, A at the A there's only liquid, and just below the A in the mushy zone the solid will start forming. And when the solid start forming, which will first come as a solid? copper, because copper melting point is less. So solid will be like chunk of copper here. Okay, but largely predominantly inside the liquid pool. So what we can say? What is liquid here? Nickel, because nickel is having the higher melting point, 1452 degrees Celsius. So larger will be the fraction of nickel. That's what I have written here. The percentage of nickel in the solid will be very high, but upon decreasing the temperature as the solid is growing, percentage of nickel in the solid keeps on decreasing because it's converting into the solid, and the approach is towards the overall composition, and it approaches towards the overall composition C naught. Okay. At high temperature, a phenomenon called the diffusion appears in the material, according to which nickel diffuses from center towards two outward directions. So what happens at a higher temperature? There is a phenomenon that we call as the diffusion process in the material. According to diffusion, the nickel will diffuse from center. So So, what I was saying, at the higher temperature, a phenomenon called diffusion appears in the material, according to which the nickel diffuses from center to the outward direction. So, nickel will diffuse from center to outward direction. This is the nickel, okay? And copper diffuses inward, and copper will diffuse from here to inward direction, okay? It is said that every 20 degrees Celsius increase in temperature, diffusion multiply by 2. Okay, that we have already done. During the Massey zone, due to Massey zone, solid will nucleus at the thousand of places in the liquid metal. And as this solid nucleus is growing, each and every solidification front will have a particular orientation of the atom. Okay, so I have already told solid is nucleating here, and here. So that is what I have written. Solid is nucleating at thousand of places in the liquid metal. In the liquid metal, okay. And every solidification front means this outside boundary will have a particular orientation of the atom. So this solidification front may be having the particular direction like this may be having like this direction and this direction, okay. So they are having the different orientation of the atoms. The moment the temperature of the material slightly goes below the solidus line, solidus line, so this is the Massey zone, and the process is going. So the moment we go down like here, so it will become 100% solid. So what happens, these solidification front will grow, these all will grow, and they will mix. The solidification front will mix here, and they will form a boundary that is called the grain boundary. The different solidification front will combine together, and entire material will convert into the solid phase. The region in the material where different solidification front are fusing, there will be mismatch in the orientation of the atom. Okay, so the region of orientation of mismatch, so the we know at the way where the solidification front are meeting, there will be mismatch in the orientation of the orientation of the atom, and this mismatch orientation atom is known as the grain boundaries. At the grain boundaries, the bond length will be larger. Okay, so what happened at the grain boundaries, the bond length, suppose this is the grain boundary, suppose. So we know the each solidification front has their own kind of arrangement of the atom. So let's say there is atom arranged in this direction, and here the atom is arranged like this, here like this. So atom is arranged is differently here, and here, but they are all meeting at the boundaries that we call as the grain boundary. And at the grain boundary, the bond length is larger. So bond length is larger means they this is having the less energy to break. So that is what I have written. It can easily be broken. That is why it is said that grain boundary are at the higher energy level. So one which you can easily break means they are unstable, means they are having higher energy. So since it is very prone to breaking, broken can be broken. So atmospheric oxygen first attacks the grain boundary atoms and corrodes the material. So whenever the atmospheric atom will attack first at the grain boundary, because it is the grain boundary where the bond length is higher. The atoms are at a high energy state, at high energy level, and they can easily be broken. Now, to increase the corrosion resistance of any material, we add chromium in it. Why? Because chromium, after reacting with the atmospheric oxygen, it produces the chromium oxide. Being foreign element, the chromium oxide is a foreign element. Chromium is a foreign element. So chromium oxide gets accumulated at the grain boundaries. Why? Because it is the grain boundary where the bond length is high. So it will get accumulated at the grain boundaries. Now, since at the grain boundary there is a huge space, void space, the bond length is high. Now we have chromium oxide at the grain boundary. Therefore, this prevents the grain boundary corrosion, because now oxygen will not come and attack here. Because why? Because oxygen is already taken by the chromium to form the chromium oxide, and it will get accumulated at the grain boundaries. Nickel and stainless steel is a phase stabilizer. Okay, phase stabilizer means something which you add, then it will give more stability. Okay, so suppose this is our grain boundary, and at the grain boundary, chromium Cr2O3, that is chromium oxide, will forms on the grain boundary itself. There is other term which you call as the coring or miscibility cap. What is the coring or miscibility cap? When the same sample of copper and nickel is cooled rapidly, since there will no any time, since there will not be any time for diffusion to take place, because when the copper and nickel is cooled very rapidly, there is no time for diffusion. So there will be concentration gradient of nickel within the grain. So there will be concentration gradient of nickel. Why? Because it is having the higher melting point. There will be the concentration gradient of the nickel within the grain. At the grain boundaries, percentage of nickel will be very low. So because the nickel concentration gradient is inside the grain, there will be concentration gradient of nickel within the grain. What do you mean by the concentration gradient? Means somewhere there will be high nickel, somewhere there will be less. So there is a concentration, basically gradient. Gradient means change over the length. What is gradient? Gradient means change per unit length. It is not constant. Okay, gradient means suppose this is the x length, so there will be change per unit length. Okay, so there will be the concentration gradient of nickel within the grain. So at the grain boundaries, percentage of nickel will be very low, because we know nickel is diffusing from inward to outside. So if you do the process very fast, what happen? Diffusion will not take place. So nickel will be accumulated at one place. So there will be concentration gradient, which means at the grain boundary there will be no, or there will be very less nickel. It can be seen in the phase diagram that lesser is the percentage of nickel in the alloy, lower will be the melting point of the material. So if you look at the phase diagram, then if the nickel percentage is less, then melting point is of the material is less. Why? Because lesser. So we know the diagram is like this. Here is the nickel 100 percentage. So lesser nickel percentage means somewhere here. If somewhere here, then we are already having the lesser melting temperature like this to this. Okay. If the nickel was high, the melting point would have been like this. So this is having high temperature than this. Okay. So upon hot forming, so what is happening? So it is happening. So what I have said is that simply it can be seen in the phase diagram that lesser is the percentage of nickel in the alloy, lower will be the melting point of the material. Okay, so upon hot forming such material, grain boundary material will melt out, producing the crack, which leads to brittle fracture of the material. This phenomenon is known as the coring or miscibility gap. So what is coring or miscibility gap? Coring gap or miscibility gap is simply when when we do not allow the diffusion to take place, or when we solidify at very faster rate, the nickel will not diffuse. The nickel will be gradiently, there will be gradient in the concentration of nickel, which means somewhere it's high, somewhere less. So at the grain boundary, nickel will be very less. So nickel percentage is very less means at grain boundary the melting point is less. So when melting point is less, then when we are hot forming, when we are hot forming means when we are heating the material and doing the rolling process. So when we are hot forming, so the temperature may be such that the hot forming temperature is greater than the melting point what is required at the grain boundary. So that may happen, and if the hot forming temperature is greater than the melting point, which is basically at grain boundary, the melting point is very less, this material will go the fracture. Okay, so this there will be little there will be brittle fracture of the material. So brittle fracture of the material because of the hot forming process, because of the no diffusion or less diffusion, or because of the at grain boundary melting point is less, is known as the coring or miscibility gap. So binary phase diagram of type 2. We will now study the binary phase diagram of type 2. Material that are completely soluble in liquid state but partially soluble in solid state means type 2 means that kind of material which is 100% soluble in the liquid state but only partially soluble in the solid state, that we call the type 2 material. Okay, when something is completely soluble in the liquid as well as in the solid, we call it a solid solution. But here we do not call solid solution, we call the solid solubility. Okay, what we call solid solubility, and here we call the solid solution. So one of the example of the type 2 is the lead and the tin. For the lead and the tin, we need to study the diagram. Suppose this is the vertical lines. Okay, these are the vertical lines. And here the diagram will go like this. Okay, and here will be the liquid, and here will be the alpha phase, and here will be the beta phase. Okay, and this liquid is coming and getting turned into the alpha plus beta. And at this point, if you look at here, this is liquid and there is alpha phase, so there will be alpha plus liquid phase. The liquid phase and going this is the just a point. Okay, if we follow this point strictly vertically down, we see liquid is directly converting into the alpha plus beta. So it is always 100% true that whenever there is a type 2 material means partially soluble in the solid and completely soluble in the liquid, then there will always be at least one point in the phase diagram where liquid is directly converting to the mixture of two solid. Okay, means mixture of two solids. It's not a simple single phase, it's a two phase kind of thing. So solid solubility we call it. Okay, so this point is known as the eutectic point. Okay, so we have to now mug up the temperature limit. So for the tin, the temperature at this point is 327 degrees Celsius. The tin melting point is 327 degrees Celsius, and for the okay, sorry, for the lead it is 327 degrees Celsius, and for the tin I have missed the temperature limit here. You can refer to some book or internet. Now here this point. Okay, so this horizontal line temperature is having 183 degrees Celsius. Okay, so we have to remember this horizontal line is 183 degrees Celsius, and here we have 327 degrees Celsius, and the fraction. Okay, here the lead is 100 degree 100 percentage, here the tin is 100 percentage means if you go from here to there, the tin percentage is increasing from 0 to 100% here. Okay, and if you go from here to here, it is the lead which is 0% here, and the lead become 100% here. Okay, so what it is the alpha phase, and this point is having the 18 percentage. We have to remember it is 18 percentage, and this is the 62 percentage, and this last point is the 97 percentage. So we have to remember 18 percentage, 62 percentage, and 97 percentage. What? 18 percentage, 62 percentage, and 97 percentage. Okay, so I will draw a diagram for you. So wait. So basically what we are drawing a simple diagram. So what we are doing like this. Okay, so this line temperature is 183 degrees Celsius. This is 327 degrees Celsius. This you refer to the book, please. And here we have alpha phase. Here we have liquid phase. Here we have beta phase. And so what will be here? Here will be liquid plus alpha. What will be here? Liquid plus beta. What will be here? From just if we go follow this particularly alpha plus beta. This is known as the eutectic point. Okay. Look here. What is the alpha phase? Alpha phase is 18 percentage of what? You go from 0% here, 18% here. What do you mean? Lead means alpha is the solid solution of tin and the lead, and the maximum 18 percentage tin can be dissolved in the lead completely. So alpha is a phase. It is the solid solution. Alpha since is a solid solution. Why solid solution? Because single phase. Okay. So it is the solid solution of tin and the lead, where a maximum 18% lead can be dissolved in the maximum 18 percentage tin can dissolve in the lead completely. This solid solubility decreases by decreasing the temperature. Beta phase is the solid solution of lead and tin. Solid solution. So what is beta? It is the solid solubility, we can say, because not 100%. This is a kind of type 2, so we can use solid solubility also. It is the okay, so it is the solid solution of lead and tin, and maximum 3% lead can be dissolved in tin completely. So maximum 3 percentage of what? 3 percentage, what is going to become 100% here? The lead then means from 0 to 100% means here what is the percentage? 3% means maximum 3 percentage lead can dissolve in the tin for the beta phase. Now, any line on the phase diagram that separates a single solid phase with a mixture of solid phase is called the Solvus line. So, Solvus line means what? Any line that separate the liquid phase into a two mixture phase. So, this is the Solvus line. So, where is Solvus line? Is this the Solvus line? So, see why? It is because this is such a line which will separate one solid to a mixture of two solid. So this alpha is a solid, beta is a solid, and here alpha plus beta. So this is a solvus line. This is a solvus line. Single solid phase with a mixture of two solid phase, known as the Solvus line. And plant family has two children. We already know, and this is called the Gibbs modified phase rule, because for Gibbs modified phase rule, P plus F equal to 2 plus C. But here in the phase diagram, phase diagram, we replace 2 with 1. So it's not the plant family has two children like we have studied. P plus F equal to C plus 2. But here, since we are talking about the type 2, so now this is phase diagram. So in phase diagram, the two become one. Okay. Mm. Eutectic means U means nice, tectic means melting. So eutectic means very nice melting. Liquid going to directly to the two solid. That's called the eutectic point. A eutectic point, what we are having? Degree of freedom equal to 0. Because why? Because what we have make the diagram like this. So this is eutectic point because here the degree of freedom is 0. This is the totally invariant. Okay, point. When there is a partial solid solubility, there exists one point on the phase diagram where liquid directly converts into the two different solid without appearance of messy zone. That's called the eutectic point. Because if you see here, there is no messy zone. Okay, one liquid directly goes to solidify into the alpha plus beta just at an instant. Okay, so it's a point. Degree of freedom is equal to 0. No messy zone. Without them, okay, ठीक है. It is an invariant reaction, means degree of freedom is 0, and at any invariant point there three phases will be in equilibrium. So whenever there is a degree of freedom equal to 0, this means three phase will exist in equilibrium. All the binary phase diagram are plotted at a single particular pressure, and the moment pressure is changed, the shape of the phase diagram will change. So whatever we have studied, this diagram of lead and nickel, or earlier we have studied about the copper and the nickel. Here we have studied the lead and the tin. So these diagrams are drawn at a particular temperature pressure. Okay, once we change the pressure, the diagram will change. Okay, now we are going to calculate the mass fraction of the phase present in the alloy of lead and the tin with 35% lean at the 184 degrees Celsius. So there is 18% degrees Celsius, so I will again make the diagram for you. What happened? Oh, sorry. Okay, so come here. So like this we have make the diagram. So here we have 18%. Okay, we have to remember 62 percentage. What is here? 97%. Okay, so written here at 18% 62, and here it is a 97 percentage. So this is the 107 183 degrees Celsius line. Okay, now it is saying 184 degree, means we have to go above. So like this, but very near to 183. Okay, so when we are going, this line is cutting this and this. Okay, it is already 62, means there is 61. We have given 35%, means the line is in between. So if the line is in between, let's say we are using the color like something like this color. Okay, so in 35 degrees Celsius may come in this in middle. So this line is dividing the red line in this fraction and this fraction. Okay, so now we are going to find the mass fraction of phase present in the alloy of the lead tin. So what are the phase present here? This will be liquid. Okay, so this will be alpha plus liquid. Okay, so alpha is here and liquid we are going from here. Okay, so what is the alpha page? For alpha page, opposite we have to move. So this, so 62 minus 18, 62 minus 18 divided by 62. Okay, the 18 is here. Sorry, this is what 35. So 62 minus 35 divided by 62 minus 18. This is the alpha phase. Okay, so alpha phase is equal to 62 minus 35, 62 minus 18. Okay, this is this much. What is liquid phase? 1 plus means alpha phase plus liquid phase equal to 1. So simply subtract from the 1, we get the answer. That's it. Now we will study the iron carbon diagram. Before we going to study the iron carbon diagram, I would like to say I would like to conclude our chapter this.